Today, let's continue with the matrices that has been taken already. In my previous class, teaching matrices, I explained what is a matrix, what are the types of matrices, and also about determinant and finding the inverse of a given matrix. These things were taught in my previous class. Now today I am going to take a different concept in matrices. Here a problem is given to you. Before taking up the problem, I want to explain about what is called the rank of a matrix. See, if I let A be equal to your M cross N matrix, what is the meaning of this? This is an M cross N matrix in the sense that there will be M rows and N columns. As I have already explained that this represents a matrix in which the elements are A11, A12 up to A1n, A2n, A21. See, actually the expansion of this will be equal to your A11 dot dot A1n and A21 dot dot A2n, and it goes on like this, and you get the last row to be AM1 AMN. So this is the matrix. This is, in fact, this is a matrix. I call it as a matrix because the number of rows is not equal to number of columns. So it is not a square matrix. If it is a square matrix, then the number of rows must be equal to number of columns, and we call it as a determinant also. Okay. Now, so this is the meaning of this. Now I am going to introduce a new concept, or I am going to explain to you a new concept called the rank of the matrix A. See, rank of matrix A, that is, I write it as row of A, or even in some books we can find R of A. See, by this row of A I mean the rank of the matrix A, or R of A. See, what is that we do here is how, before explaining fully what is the meaning of rank of matrix, I have to necessarily tell about what are called the minors of a matrix. This concept or the idea of minors have also been explained in my previous classes. Now you see that if you are having, let us suppose that you have got 1, 2, 3, 4, 5, 6. This is a matrix. This is a matrix, and you see that minor means I can take this 1, 2, 4, 5. This is a minor, and 1, 3, 4, 6. This is a minor, and this is 2, 3, 5, 6. These are called the minors of the matrix. So this is a matrix, and the minors of the matrix is given like this. It can be even here got 2 cross 2, it can be 3 cross 3, and it can be 4 cross 4, depending on the matrix that you take. So you can make any number of such minors, and we call them as submatrices also. What I am going to tell you now is that you collect all it is not that much easy to collect, but procedure wise or the explanation wise, what should I tell you is that you collect the minors. It may be a 2 cross 2, it may be a 3 cross 3, or it can be a 4 cross 4, according as the matrix that is given to you. Then you collect or you pick the matrix, that is the submatrices or the minors, and find out the determinant value. What is the meaning of determinant value of this? This is 1 into 5 minus 4 into 8. This 4 into 2. That is called the value of the matrix. That is the determinant. You find the value of that. If it is not equal to 0, if it is not equal to 0, then we say that the rank, see the rank of this is, now you will find, what I am telling you is that you will find all those submatrices, pick those submatrices. This we call it as the order of this submatrix is 2, the order of this submatrix is 2, the order of this submatrix is 2. Whereas the given matrix A is of order 3. See, it is a 2 cross 3 matrix. This is a 2 cross, this is a 2 cross 2 rows and 2 cross 3 matrix. This is a 2 cross 3 matrix, and this is of order 2, this is of order 2, and this is of order 2. Now you see that here we say that if that is you pick all those submatrices and find out the determinant value. If the value of the determinant becomes 0, then this cannot be the rank. What I mean is, here you have got here the rank of this to be 2, here rank of this, here the that is the order of this is 2, order of this is 2, order of this is 2. If you suppose that the value happens to be 0 for these submatrices, then we say that this is not of order, that is rank 2. This is not of rank 2. We go pick like that, but we choose that rank of a matrix means the rank of a matrix is that positive R, which is the order of that matrix determinant which is not equal to 0. For higher orders it will be 0. What I mean is that, see here you see that this is non-zero. These are all, you find that these are all actually non-zero. But as such, if you take this A, you see that this is of order, this 2 cross 3, and the rank of this A can be the minimum of these two. Fine, bear that in your mind that this A is a matrix of order 2, 3. That means 2 rows and 3 columns. And if you are going to find the rank of this matrix, then the rank of this matrix can be minimum of the rows and columns. Here what is that minimum? Number of rows is 2 and number of column is 3. Therefore, the rank of the matrix at the maximum will be the minimum of 2 and 3. It can be only 2. So it so happens, you can very well find. You see that here you find that none of these submatrices are equal to 0. What is the order of these two? It is 2. Order of this, every matrix here is submatrix is 2. Therefore, the rank of this matrix is A is 2. So I will repeat this. Just let me not elaborate too much on things again and again. I will just tell you that if a given matrix A is m cross n, if a given matrix A is of order m cross n, then we collect all those submatrices and find out the determinant value and see whether they are zeros or non-zeros. Keep that in your mind. Then now I define what is that rank. Rank means it is a positive integer. Know that it must be a positive integer and it is the order of that submatrix whose determinant value is not equal to 0. But at the same time, for higher order or plus 1 or plus 1 and more, the determinant value will become 0. That means here you see that all those submatrices with order to R will not be 0. At least one submatrix of order R will not be equal to 0. But for higher values, R plus 1 and more, all those submatrices with the order R plus 1 and more, they will become zeros. If that happens, then we say that R is the rank of the matrix. Okay, now so here it is very simple that here you have got what A is equal to so much, and you are having this, none of this, see here it is not equal to 0, here it is not equal to 0. What is the order of this? That is equal to 2, and therefore the row of the, that is the rank of this A, rank of A will be equal to your 2. And how is that? And another point that you must know is that here the rank of any matrix will be equal to minimum of the rows and columns. That means row of A will be equal to minimum of 2 and 3. Now you find that it is equal to 2 only. Okay, so this is all about. So if you want to define the rank of a matrix, given matrix, it is nothing but a positive integer R, which refers to the order of at least a submatrix whose determinant value is not equal to 0, but for higher orders R plus 1 and more, the determinant value will become is 0. So this is the definition of the rank of a matrix, and rank of a matrix plays a very important role in determining the consistency of a matrix. By consistency, I mean solving a given system of equations. So you see that here you are given a system of equations. Now whether this system of equations can be solved for x, y, z is determined by the rank of the matrix. Okay, so this plays a very, very important role. See, I will tell you what it is. Now here, so you have understood what is the meaning of the rank of a matrix. Now let us start applying. I will do a problem how to find the rank of a matrix. I will tell you how the rank of a matrix. I will choose my own problem here. See, let me take this 1, 2, minus 1, 4, 1, 0, 2, minus 4, 1. See, let me suppose that this is a 3 cross 3 matrix given to you. Now what is that? A is a 3 cross 3 matrix. This implies that row of A, at the maximum it can be equal to only 3. So rank of the matrix is definitely 3. It can be 3 or it can be less than that. Okay, now it can be 2, it cannot be 1, it has to be 3 or 2, like that. Now how to find the rank of the matrix? That is a question. Now how do we do that? See, take this A. What you have to do is, in matrix, matrix row operations and column operations will not change the nature of the matrix. For example, what I mean is that if you multiply this, the first row, by a quantity, or you multiply and you subtract it from the second row, or you repeat with the first, repeat the process with columns also, or columns and rows combined, you see that the nature of the matrix will not change, and it will not alter the rank of the matrix also. If the rank of matrix happens to be 3 or 2, whatever it be, then you see that by doing all those operations with row operations or column operations or both combined, you see that such operations will not alter the rank of the matrix. This is point number 1. So first point I told, number 2. First point I told you that the rank of the matrix will be at the maximum 3 only, minimum of the rows and columns. So here it so happens that the number of rows is equal to 3 and the number of columns also equal to 3, and that the rank of the matrix at the maximum can be 3. So this one. Then you see that if determinant of A is not equal to 0. What is that? determinant of A is not equal to 0, this is called non-singular matrix. What is this is called? Singular. This is called non-singular matrix. If it is a non-singular matrix, then row of A is equal to what? It is equal to the order of matrix. See? Order of matrix. So you see that here you see that 3 cross 3 means if the determinant value is not equal to 0, you see that it will be equal to your matrix. That is the order of the matrix. Now order of the matrix in the sense that if it is here it is 3 cross 3, that here it is 3, therefore the rank of the matrix will be equal to 3. Let us check that. And also when you are going to now you see that method of finding the rank of a matrix, I explained to you in the initial or at the beginning itself that you are going to pick all those submatrices and find out the determinant value. And you will search, and if you come across for a particular order of the matrix, submatrix, if the determinant value is not equal to 0, but for higher orders the determinant value is 0, then that particular value, say R, will be called as the rank of the matrix. This is what I explained to you. Now, so you see that. Now, so what is the method of doing it? You will pick all those submatrices. You will pick all. Here, what are the submatrices? 1, 0, minus 4, 1. It is a submatrix. And 2 minus 1, 1, 0. It is a submatrix. 4, 1, 2 minus 4. It is a submatrix. So you pick all those matrices, and you see that you try to find out the determinant value. And you will. This is a cumbersome or a difficult process of doing it. So here it is 3 cross 3 with simple numbers that you have got. So writing the submatrices and finding the value may be comparatively easy. But if you are going to have a a big matrix, and if you are asked to find the rank of the matrix, this type of process will not lead you to a result. It will frustrate you or complicate you. You cannot be successful in that. So we go for some other way of doing it. So what we do is we try to bring it to a upper triangular form or a lower triangular form. Upper triangular form is the one where the upper triangle means, see, this is called your principal diagonal. Above this principal diagonal, if there are elements, and below the principal diagonal you have got 0, it is called upper diagonal matrix. Say upper diagonal matrices will be like this. See, it is 1, 2, it is, let us suppose that 4, I will write like this, 4, 1, 2, 3, 1, here it will be 0, 1, 5, 0, 0, minus 1. Yeah, this is, here it is 3, 3, yes, minus 1. This is your principal diagonal. This is your principal diagonal element. Now below the principal diagonal elements you have got zeros, and above that you have got elements, non-zero elements, means it's called upper diagonal. Let's see, upper triangular matrix. Upper, I'll write it here. It is upper So it is called upper triangular matrix. And if it's a lower triangular matrix, means what? You will have elements at the bottom and zeros on the top. So we will try to bring it to that form, an upper triangular or lower triangular matrix, and then decide on the rank of the matrix. So first thing that you may check is that you can go for finding the determinant value of this. If the determinant value of this is non-zero, you can very well say that the rank of A is 3. The rank of A is 3. by chance you are having it. No, it is not so. It is not so. Then what you have to necessarily do is you have to go by the process, long process of what? Finding the submatrices and then finding the determinant value. That will be difficult. So what we do now is that we go straight away changing the given matrix to upper or lower triangular matrix, and then decide and then conclude about the rank of the matrix. Now I'll tell you how that is done. See, and I told you that a matrix nature is not changed, or the rank of the matrix will not get altered. Rank of matrix, see, rank of a matrix will not get changed if rows and column operations, rows and columns operations are carried out systematically. So if that is the rank of a matrix, nature will not change. So the rank of a matrix will not get changed if rows and column operations are carried out systematically. If you do that, it will not change. See, for example, I'll tell you here it is how it is done. So let us come to this. See, let me change this. See, how will you do this? See, I will put it like this. You take this A and keep like this 1, 2, minus 1. I will go for upper triangular matrix in the sense that the principal diagonal is there. Elements above that will be non-zeros and below that will be zeros. How to do that? You keep this. See, I will keep this R1 and I will write it as R2 minus 4R1. What does it mean? Multiply this. See, multiply this by 4 and subtract R2 minus 4R1. That is 4 into 4. 4 minus 4 is 0. Then 4 into 2, 8. 1 minus 8 is minus 7. 4 into minus 1 is minus 4. Take away from this, it is 4. Can you catch what I am writing on the board? R2 minus 4R1 means every element, see, you multiply the first row by 4, every element in the first row, and subtract it from the corresponding elements in the second row. Are you able to catch? Multiply the first row by 4, every element in the first row by 4, and subtract it from every element in the second row, the corresponding elements. Therefore, you will get it. Same way I will write R3 minus, I must get rid of this 2. So, 2R1. See, I will try to bring the first elements of the second, third, fourth row all become to 0. The method of doing it is that you try to keep this as 1. Even if you do not have 1, you try to do something. You can change the rows into, that's why I told you, you can go for row or column operations, in the sense that you can change the rows to column, that is, you can change first row to second row to third row. You can just interchange them, and so that to make the problem easy for you to get the triangular matrix. Are you able to catch? What is that you will do? You can go for interchanging the position of the rows, interchanging the position of the columns, so that you will get convenient number which will enable you to successfully get what? Here the triangular, the upper triangular matrix, in the sense that the elements are non-zeros above the principal diagonal, and below that they are zeros. So this is my this thing. So you see that what is that I have done here? Since it is lucky that I am having here 4, 1, it has become easy. Otherwise, that particular element must be made as 1, either by dividing the row by some number. For example, let us suppose that you have got 5 10, 15 like that. If you want to make this as 1, you divide this first row by 5, so that you'll get what? 1, 2, 3. So you're successfully making this as what? 1. Or let us suppose that you have got 5, 8, 11, and here you have got 1, 6, 7. Then change this row, interchange the rows. Take the second row to first row and first row to second row. Thereby you are getting the first element as 1. Now it has become easy for you to get the what? The upper triangular matrix. Are you able to understand? So this is the way that we do. Okay. So now what we do is, here you come to this. Now you see that this is 2. Now what is that I have done here? R3 minus 2R1. Multiply the first row elements by 2 and subtract it from every corresponding element in the third row. So what will happen here? 2 minus 2 is 0. Here 2 into 2, 4, subtract means you will get 8. And here it is minus 2, subtract means you will get it as 3. Am I correct or not? So you see that I am doing very simple technical work. I am doing in the sense that I am trying to do some technical job here, but at the same time they are only simple. So what is that I have got? I have successfully got this. Then what I do now is that, see, here I have got a new matrix, and now let me take this 1, 2, minus 1. You can do anything that you want, provided you try to bring it to your upper or lower, upper triangular form. So here what I do here is that, see here, 0, it is minus 1, it is 4 by 7. So this R1 remains the same. R2 is divided by 7, and keep this as minus 8, 3. Are you able to catch what I am doing here? So everything, I am writing everything A, because A is not changing. Otherwise you are doing some manipulations, this A may change, but I am telling you that A will not change. A matrix will not change, its nature will not get changed. So you see that I write only this. Now you see that, now can you understand how I was explaining a concept here? Now you see that in order to get rid of this, because I must bring a triangular matrix 0, 0, 0 like this principle. So this I must get it as 0. How to get at this place 0 means, if I have 1 at this place, I can make it as 0. Otherwise I cannot do. So what I do here is that I take the second row and divide throughout by 7. So 7 by 7 is 1, therefore minus 1. Divide this 4 by 7, so we will get 4 by 7 and retain this. Then I write this. It is 1, 2. You keep this R3 as 3. So this is 1, 2, minus 1. This is R1. And this is 0, minus 1. 4 by 7, this is R2, and then I write it as R3 minus 8 into R2. See, what is that I have written here? R3 minus 8 into R2. Now that means what? Here 8 into 0 will be 0, so this will be 0. This is 8 into minus 1 is minus 8. Minus 8 minus of minus 8 will be 0. See, what is that I have done here? It is minus 8 minus, multiply this by 8. So it is minus 1 into 8. So minus into 1 minus will make it as plus. So 8 plus 8 is equal to 0. So you see that this will become minus 8, this will become plus 8. So this becomes 0. So this element will be 0. Now I am getting, see I am getting this 0. See, principal diagonal element is here. Principal diagonal. And what is the next one that you will do? So 4 by, multiply this by 8 now. Multiply this by 8, it is 32 by 7. And 3 minus 32 by 7. So this is equal to what? It is 21. 21 minus 32 will be what? It is 21. It is 11 by 7 minus. So what is that I am having here? Minus 11 by 7. So what is that I am having here now? So you multiply this by 8 and subtract it from the second row, third row elements. So this will be minus 8. Minus 8, minus of minus will be plus, so this will be 0. And then you see that this will be 4, 8 into 4 is 32, 32 by 7. 3 minus 32 by 7 will be 21 plus 22 plus 32 minus 11. So this place will be what? Minus 11 by 7. It is minus 11 by 7. Now you see that this is minus 11 by 7, and therefore still further, see, this is the upper triangle matrix. Can you see this? See, this is your principal diagonal element, and above the principal diagonal you have got non-zero elements. Below the principal diagonal you have got 0. So bring it to the upper triangle. So I am able to bring. Now you see, now the other way of doing is, it is still more, it is there. What is that they will do is that you go for other, see what they will tell you, no, you will go for other modes, you go for a column operation also. So you go for column operation in the sense that you divide this by 2. Divide the second column throughout by 2, so that what is that you will get here 1, then take away 1 minus 1. So you see that this process of row operations can be carried out with the column operation also, so that what that you will get finally is that there is a chance that you will get like this, that is I1. It will be what? I1 3 in this particular case. I am telling you, I am sure that further simplification or further trial of doing things is not possible, because this is the maximum. Even if you try to bring zeros and everything, you will see that end up here. That is what is to be done here is that ultimately, while finding for finding the rank of the matrix, you must bring it to be a unit matrix, in the sense that unit matrix will be, for example, it will be like this. It will be let us suppose that it is I2 0 0 0. That means what? Here everywhere it will become 0, but there will be one matrix, sub matrix here, which will be 1 1. This will be of the form what? It is 0 1 1 0 0 1. What I mean is that you try to bring this to a unit matrix form, so that it will be of the form what? IR2 0 0 like this, and here I2 it refers to a 2 cross 2 unit matrix. 2 cross 2 unit. But in the rest of all other places you will have only 0 matrix. Say this part will be 0, this part will be 0, this part will be. So this will be called as your what? So this tells you that this is the rank of the matrix. This is one way of doing it. This is what? This is naturally a perfect way of doing it. I don't say no. But coming to this place, I find that I will define rank of a matrix in another way also. How do I define? Means do all these operations to get your upper triangular or lower triangular matrix. Then after completing that process, find out how many are there. That is, how many rows or 0 elements. How many rows have non-zero elements? Are you able to understand? In the sense that do the process column row operations, and finally arrive at the upper triangular matrix like this, and find out. Now check how many rows are non-zeros. Non-zeros in the sense, see, the first row you take, it is non-zero. At least in the second row you see that it is non-zero. The third row means what? At least there is one element which is non-zero. Can you understand? So you see, must have non-zero elements throughout in a row. You find out how many number of rows are there with at least one non-zero element. See, in the first, all the 3 elements are non-zeros. In the second, 2 elements are non-zeros. At the third one, at least there is one element which is non-zero. Therefore, I say that here count how many number of rows are have non-zero elements. 1 2 3 rows. Therefore, the rank of this matrix is 3. That means this implies that row of A is equal to 3. Therefore, the rank of the, so The other way of effective way, I'll say that it is not required to go through the rigorous process of bringing that unit matrix. It is not required, actually speaking. If you, that is the way. I don't say that it is not. You have to, if you are doing it systematically, means do that. But what I'm telling you is, if you're going to decide even finally you're going to get the same answer, nothing more. It is not going to be in no way, it is going to be different from what I am getting here. So here I can stop. I can very well and stop. If I come to a stage where further bringing zeros is not possible in any row, here I cannot do anything. I cannot bring this as 0. How can I bring it to be 0? Because it is not possible. Because you are going to multiply this and subtract or something like that. Do some operations. That means if you are going to do an operation with an row, that operation must be carried out with every element in the row in which you are going to do it. In the sense that if you are going to multiply this and subtract the elements from the second row, means every second row element must subtract the element that I have got. So you see that it is that lead you to some numbers. So it is not possible. It is actually not possible. So I am sure that further things cannot lead me to a different result. So I can stop. So even if I stop at this stage or try to bring it to unit matrix form, then also you see that the both of them will give me the same value. The rank of the matrix will remain there. It is not going to change. As I told you, your row operations, column operations, or both combined will not change the rank of the matrix. Are you able to understand? So you see that I can stop at this stage and count the number of rows, non-zero rows, in the sense that at least one element in that particular row must be non-zero. So we call this a non-zero row. So find out how many rows have non-zero elements. Then that will say that is the number of rank. What is the rank here? 3. Now the rank of A is 3. Another one, another checkup is that. So here you see that the rank of A is equal to 3. Another way I told you that another way is that here you see that what is the rank of the matrix here? That is the determinant of the matrix. 1 into 1 is 1 minus 0. Minus 4 into 0 is 0. Then minus 2 into 4 into minus 4 is minus 16. Minus 2. Okay. Then plus of minus 1 into here it is. It is minus 2. It is 4 into 1 is 4. 2 into 0 is 0. Minus of minus 1. Plus of minus 1. 4 into minus 4. Minus 16. Minus 16. Minus 2. So this is equal to 1 into 1 is 1. It is minus 8. And this is minus 2. Minus 16. Minus 18. It is plus 18. So whatever it is not equal to 0. So when it is not equal to 0, what is the rank of the matrix? The rank of the matrix is the order of the matrix itself. What is the order of the matrix? 3 cross 3. So it is 3. So I am getting this also to be 3. No, I got the row by systematic finding also. I found the rank of the matrix to be 3. So this decides. Now I told you at the beginning of doing the problem that the rank of a matrix plays an important role in deciding the consistency of the equations. Can you understand? Now you see that here you have got this. See what is that you have got here? This is called system of equations. System of equations involving x, y, z. What is the meaning of telling that solve the system of equations? Solve the system of equations means you have to solve for the values of x, y, z. Given it, these are all unknowns. X, y, z are all unknown, and you have to now solve. You have got many methods of solving this problem. Okay. Now what it tells you is that now how the rank plays an important role. I want to emphasize only on that. How the rank plays an important role in deciding the consistency of this equation. See, for example, you see this here 5, 5x plus 3y plus 7z is equal to 4. And this is equation number 1. 3x plus 26y plus 2z is equal to 9. This is 2. And 7x plus 2y plus 11z is equal to 5. This is 3 equation. This can be written as 5, 3, 7 and 3, 26, 2, and this is 7, 2, 11. This and x, y, z is a vector is equal to 4, 9, 5. So you see that, how do you get this? So this is nothing but your ax is equal to b. This is your a, this is your x, and this is your b. Now you see that you have to solve this equation. You have to solve the system of equations in the sense that you have to find the values of x, y, z. Now you can go for, I told you there are many methods of doing this, solving the problem. The first method you would have studied, that try eliminate any one of the variables using the first two equations. Then using the second and third, or 1 and 3rd, eliminate the same variable. Then it will reduce to the simultaneous equation involving two variables. Then you equalize the coefficients of the one of the variables. Then get rid of it and get the value of the third variable. Substitute in the that is the system of equations with two variables, and you get the value. Getting two values, substitute in any one of these three equations, you will get the third value. Can you understand? This is the simplest way of doing the problem. Okay, now that is a straightforward way of doing the problem. We have got other methods of also doing, but I will come to those things, solving and everything. I will come to that afterwards. But I want to emphasize the importance of the rank, or the role played by this rank in solving system of equations. I have come this one. Now what I say is that here Ax is equal to B. Now this is called your matrix A. This is called your matrix A. And what do we do here is that here this is called augmented matrix. This is called augmented. This is called the augmented matrix. What is this? AB. I'll write it here, AB, like this. AB. This AB is called your augmented matrix. Now take this augmented matrix. Take this augmented matrix and find out the rank. What is the meaning of finding out the rank? Rank means, just now I told you how to find the rank. Find out the rank. Let us suppose that you are getting the rank of A is equal to rank of AB. What does it mean? The rank of this matrix A matrix is nothing but collecting the coefficients of the x, y, z and forming a matrix. Can you catch what I am telling you? What is that A? A is nothing but a matrix formed with the coefficients of the x, y, z from the three equations given. So you see that this is your matrix A, and then your B is nothing but the constants on the right hand side of the equations. So you see that this will form what is called your augmented matrix. This augmented matrix, for the augmented matrix, you find out the rank. If you find out the rank of the matrix, and if it so happens that rank of matrix A is equal to rank of matrix of B and is also equal to your n. What is n? N is nothing but the number of variables here. How many number of unknowns here? The number of unknowns is equal to 3. Can you? 3. So you see that we call this n. We will take it as n unknowns. If it so happens that your rank of A, which is equal to the rank of augmented matrix, which is also equal to your n, then it has got unique and definite solutions. Can you understand? That means what? The solution is definite for this, and if that is, the solutions are unique, then in the sense that you will have x, y, z will have what? Unique solutions they will have. Okay. Then second one is, if rank of A is equal to rank of AB, but it is less than the number of unknowns here. It is less than the number of unknowns, then you'll see that infinite number of solutions are possible. Infinite number of solutions in the sense that this x value will be equal to k. K will take a k can be given 1, 2, 3, any value you can give. So x will take any number of values. So you see that here, first point is that if rho, see it is like this. I'll put it here. So I'll write it here. If rank of A is equal to rank of the augmented matrix, they is equal to n, this implies the number of solutions is n, or n. The number of solutions are n. That is in the sense that you will have definite solutions, or that is x, y, z will have the solution. That the number of solutions of are definite. You can build it right. And n. And if rho of A is equal to rank of B is equal and is less than n, then there are infinite number of solutions. I'll put it here. If so infinite number of solutions are possible. And the third one, this is your first one, this is your second one. Third one is, if rho of A is it not equal to rho of, that is rank of AB, then this is consistent. So here that is then no solution. That means what? Inconsistent. Inconsistent equations. In this case it is consistent. Here also it is consistent. In this particular case this is also consistent. Here also it is consistent. So you see that here, what is that I want to tell you is that if rank of A is equal to rank of AB is equal to n, then the number of solutions are n and they are unique. And if rank of A is equal to rank of AB, but it is less than the number of unknowns, n refers to number of unknowns. So then there are infinite number of solutions possible. And here in both the cases, the equations are said to be consistent. The given equations are said to be consistent. The last case is if rho of A is equal to rank of A is not equal to rank of AB, then the system of equations are inconsistent and you have no solutions for that. Can you understand? So these are the thing. So this rank of a matrix decides on the consistency and inconsistency of the system of equations. We say that the system of equations are consistent if the rank of A is equal to rank of the augmented matrix, and if it so happens that if the rank is less than n, infinite number of solutions. If it is equal to n, then the n number of solutions are there, and if they are not equal, then they are inconsistent and the solutions are not there. So this is what you should understand in this particular thing. That's why I told you the rank of matrix, it plays a very important role in this, and I have taught you also how to find the rank of the matrix. And as I told you, remember this point very well. when you are finding this rank of the matrix, you have to get upper triangular matrix, as I used to suggest, to find out the upper triangular matrix. And you can stop at one place when you can find that the number of non-zero rows will say that that is the rank of the matrix. It may not be necessary to reduce to unit matrix, but the procedure is try to bring it to the unit matrix form. That is what they say, but you can stop there, but try to learn that also. But here you can stop and say that this is the rank of the matrix. So that is how you find. And regarding the rank of the matrix, you must know that if a given matrix is m cross n, then the rank of the matrix can be at the maximum the minimum of m and n. I have given you all those things, m and n. And if the matrix, that is row of the determinant of the given matrix, is non-zero, you see that the rank of the matrix is equal to the order of the matrix. Okay, and then if you are going to bring, you see that I want to insist on this particular point, that if if a given matrix, you are given a matrix, and you may get it like this. Say it is like this. That is, you are given a matrix, and if you can bring the matrix to the form I or 0 0, you know what is the meaning of it? Will be like this, or I or 0. You may bring it to this form. This is a unit matrix of order 2, order R. You know what is the meaning of this? 0 1. This is a unit matrix of order 2. This is a unit matrix of order 3. Let us suppose that you are getting I3 0 0, something like this. Then you see that the rank of the matrix is 3. That means what? You must do all this row operations and column operations and bring it to a form like this, so that this part alone will tell you that is the rank of the matrix. This is the way, but you can take it from me that if you are going to do that upper triangular matrix, you can stop at the stage and find out how many number of rows are non-zero. That number of non-zero rows will tell you that is the rank of the matrix. Okay, with this we can